Can you see the screen? Can you see this? Can you see the shared screen?
Yes, sir.
Okay, okay, and write your write your roll numbers in the chat box. Now, my today's topic is about. Although yesterday I told you that I would be discussing bivariate distribution, but after reaching home, I suddenly found that this particular topic of cumulative distribution has not been discussed yet. And therefore, I'm going to discuss this particular part first of all, the cumulative distribution or distribution function, which will be discussed for single variable case. After that, when we'll come to the bivariate section, then there also we'll discuss about distribution function and so on. But before that, we need to understand what do we mean by distribution function for a single variable case. So that as you can see, the definition is already in front of you. So if capital X is a discrete random variable, the distribution function is defined as follows. So it is a kind of cumulative function, just like you know that in statistics, whenever we talk about frequency distribution with respect to frequency, cumulative frequencies also come. So here also, with respect to probabilities, cumulative probabilities will be calculated. If the probability function is denoted by probability of x equal to small x for discrete case, its corresponding distribution function will be denoted by fx, which is defined as follows, which is probability of capital X less than or equal to small x, and it is this is the definition. I shall explain how to calculate these probabilities with respect to a given problem. Let's not talk about that. I mean, one important thing that you have to take into you have to note down is that although I have written here that x is less than or equal to small x, every time when we calculate these probabilities, remember that capital X is discrete. It doesn't mean that capital X will take any value lesser than or x. We'll take values which are less than or equal to x, but those values has to be a discrete values. And explicitly it is defined in following manner. We considered another variable t, and this t will take values, discrete points lesser than x. And for each case, we are going to substitute these t's over here, and respective probabilities will be calculated, and they will be summed up sequentially to get the distribution function fx. Distribution function has some properties. These properties are also very important, such as if fx is the distribution function, if you consider the infinity and minus infinity points, which are the abstractions, you know, because infinity and minus infinity, nobody can realize it, but these are the abstractions to ensure that we are dealing with infinity. So at those points, at infinity, distribution functions will always be zero. So if at minus infinity, at this abstraction, distribution function will be zero. At this point, f infinity, the distribution function will be 1. And if we have 2 points A and B, where A is less than B, if A equals to B, then the distribution function corresponding to A is same as distribution function corresponding to B. FA and FB, those values will be same. If A is less than B, then FA is less than FB, where A and B are any real values. Okay, so let's proceed. We shall talk about this theorem, the second theorem that I'm highlighting later on, not now, because it is the reverse of what has been defined in the previous case. In the previous case, the probabilities were given from which the distribution function were calculated. The third theorem, the second theorem actually is the reverse of the previous one. It says that when distribution function is given, how to calculate the respective probabilities. Okay, so we shall come to this particular point later on. So now to understand the distribution function, let's talk about a problem, a simple problem, which this problem is the problem is as follows. Uh, Two socks are selected at random and removed in succession from a drawer containing 5 brown socks and 3 green socks. Now, the problem here is not itself very interesting, because it may seem to you a very silly problem, and it is not a problem. It's not at all an engineering problem. But here I have selected a very simple problem to make you understand how to calculate this distribution function. So that therefore this simple problem has been taken into consideration. So 2 socks are selected at random and removed in succession from a drawer containing 5 brown socks and 3 green socks. First of all, we need to list all the elements of the sample space and their respective probabilities. Then we are going to define a random variable, which is nothing but the number of brown socks selected. It could be number of green socks also, but for this particular problem, I have considered the number of brown socks to be the random variable. You can recalculate the entire problem by considering another random variable capital Y, which will count the number of green socks. And after that, in the third part of the problem, we are going to calculate the distribution function of this random variable. We are going to calculate the distribution function for the number of brown socks selected. So first of all, let's deal with A and B. 2 socks are selected at random and removed in succession from a drawer containing 5 brown socks. What are the possibilities? The possibilities are as follows. There are only 4 possibilities. Both the socks are brown. The first drawing is brown and the second drawing is green. The first drawing is green, the second drawing is brown. Both the drawings are giving you the green socks. And I am not telling you how to calculate these probabilities. It is a matter of combination. You can do it by yourself. Probabilities of each of these outcomes will be as follows. The 5 by 14, 15 by 56, 15 by 56, 3 by 28. You can do it by yourself. Let's come to the third part. The random variable that has been defined over here is the random variable which counts the number of brown socks only. If I denote the random variable by W, then in the first case, the value of W is 2. In the second case, the value of W is 1. In the third case, value of W is 1. And the fourth case, value of W is 0. If someone is interested in counting the green socks only, then the case will be reverse. So you can do it later on. Now, we have considered another table after this. Once we get the hint of the random variable W, now we are only interested about the random variables and their probabilities. Why is it so? Because you know that, as I told you earlier, that random variable is a function, is actually a function from a sample space to a subset of set of real numbers, set of real numbers. Now here you see the random variable is taking the values 0, 1 and 2. So we have this subset, which is obviously a subset of R, set of real number. We have counted all the random variables here. Possible values are 2, 1, 0. And the respective probabilities have been calculated, which is for 2, it is 5 by 14. That means when the W, capital W is having the value 2, the probability is 5 by 14. When the capital W is having the value 1, it is coming as 15 by 28. How? Because there are 2 cases in which the count will be 1. The W will 1 over here because there is only 1 brown sock, Here also the W is 1 because there is only one brown sock. And we have calculated the probabilities. Both probabilities are 15 by 56. And if we are interested in probability of W equal to 1, that means either we are interested in this probability or in this probability. And by the axiom of probability, these are the mutually exclusive cases, because if you are getting this pair is not happening. If you are getting this pair, that pair is not happening. So this will be probability of BG plus probability of GB, and we get 15 by 15 into 2 by 56. And from there, we have got actually 15 by 28, this value. From there, we have got this value, 15 by 28. Now, therefore, it is written 15 by 28 over here. Okay, let's proceed. Just a minute. Now, once we have this, then we are in a position to find out the distribution function. To find the distribution function, what we need to do is that, first of all, we need to apply the formula. The formula above was written in terms of X. Since we have used the notation W for the variable, random variable, so instead of X, we have used W over here. So in place of Fx, we have written Fw, and by definition, which is probability of capital X less than or equal to small x, it is probability of capital W less than or equal to small w. And by definition, we have considered a real number T, which can be any real number from minus infinity to plus infinity by definition. But since we are actually dealing with discrete case, this points T will be discrete points. Now T lying between minus infinity to plus infinity means I'm saying that T is a real number. Okay, that is another way. If you don't want to write it as this, if it makes you confused about whether T is continuous or discrete, to write T is a real number. Now we are going to calculate the distribution function values for different points. Our first point was, we have 3 points, 0, 1, 2. The first point that we are considering is 0. So we are substituting W equal to 0 in this place, which is probability of, okay, I think there is a kind of mistake I have made in notation actually. This thing will be, let me rectify it right now. This will be W, and this will be also W, and this will be also W. Okay. Now, since our random variables are W actually, so if I consider F0, if I put W equal to 0, that means probability of W, it becomes probability of W less than or equal to 0. By definition, just try to correlate the two things. What is the definition? Definition is summation over T less than or equal to W PT. Now, since my small w equal is 0, so I'm writing summation over T less than or equal to 0 PT. Now, in this particular example, although T is a real number, although if T is continuous and there are infinitely many values less than 0, here we shall not consider all the other values, because T is a discrete point and the least point that we have in this particular table is 0 itself. So therefore, we have just substituted T equal to 0 over here. This is because this is the only possibility. So summation over T less than or equal to 0 PT means P0, and that is equal to 3 by 28 from the table. Then there comes F1. When W equals to 1, then we are going to calculate the distribution function value at the point W equals to 1, which means we are going to calculate the probability where W is less than or equal to 1. By definition, I am writing it as summation over T less than or equal to 1, because small w is now 1, PT. How many discrete points are there which are less than or equal to 1? In this particular case, 2. One is t equal to 0, another is t equal to 1. So we write, first of all, we substitute t equal to 0 over here, we get p0, and then we substitute t equal to 1 over here, we get p1, which such that p0 plus p1 gives you 3 by 28 plus 15 by 28 from the table, which is 9 by 14. Lastly, we have w equals to 2. So in a similar manner, we substitute w equal to 2, and which is the probability of w less than or equal to 2. In a similar manner, since there are only 3 possibilities where t can take values less than or equal to 2, so we substitute all the values one after another sequentially, and we get p0 plus p1 plus p2, which is 3 by 28, 15 by 28 plus 5 by 14, which is equal to 1. Now here is the important point. Now suppose you want to check whether you have done it correctly or not. That means if you are correct, then this part is actually very important, because the total probability, as you know, the total probability of the probability distribution is always equal to 1. So total probability will always be equal to the last value of the distribution function. Now, if the last total probability is equal to 1, so if the last value of the distribution function comes out to be 1, that means your calculation is all right. If it is not, that means you have done some mistakes somewhere in between. Maybe it is your mistake, maybe the chart is not complete at all. Okay. Two cases may arise. Suppose your total probability is not itself 1. Then this 1 will not come. That means there is something wrong in your chart. Or if your chart is complete, that is total probability is 1, but your distribution function's last value of the distribution function is not coming as 1. That means you have done some mistakes somewhere in between during the calculation. So you have to be very careful about this. Now, this is not a function actually. These are the values of the distribution function, isn't it? Now we have to write the thing in terms of function form. So how we are going to write it? First of all, first of all, let us try to, because you know these are the individual values, so we have to write this in a function form, because probability is always written in a functional form. So we are going to do the same thing with the distribution function also. So how to do this? So we have written fw over here. You see, now f of 0, which was probability of w less than or equal to 0, which was summation t less than or equal to 0, pt, which gives you p0 is equal to 3 by 28. So your lowest value of the point is 0. Now, if you consider w, if you consider the small w to be less than 0, there are no such possibilities over here. So probabilities are actually coming out as 0. You see, because as you know, in probability distribution, we write sometime we always write this kind of things. So for example, if I talk about the Poisson distribution, we write the probability is this when x takes value from 0, 1 to up to infinity, and we write 0 otherwise. Okay, that means when x is not 0, 1 to infinity, is something else. So this is the otherwise portion. This is the otherwise portion that we usually write. Okay, so when w is less than 0, the probability is not calculated. It is having the value 0, and therefore it will not affect the function at all. Now, when we consider w to be greater than or equal to 0 and less than 1, that means what? In between 0 and 1, actually there are infinitely many points. But again, I am saying that I am not talking about the continuity. I am talking about the discrete case. So here, although I am writing it in this manner, w is only having the value which is 0, because equality sign is there. So if we write W less than or equal to 0 less than 1, it actually means I'm talking about W equal to 0. Okay. We write it in this manner because when I will plot the thing, you will understand why do we write this particular thing in this way. You will understand while plotting the way when I will show the plot of the function. So, or right now I can say W is equal to 0 when probability of when the W is having the value 0, the probability is 3 by 28. Now, if you draw the graph, say for example, this point is 0 and this point is 1 and this point is 2. So these are the discrete points situated unit distance apart. Now, if this point is 3 by 28, say for example, then for 0, we are having this value over here. This is the value of the distribution function. So FW is 3 by 28. And it will remain 3 by 28 until you reach 1. When you reach 1, it takes another value which is 9 by 14. Another value which is 9 by 14. And it remains 9 by 14 until you reach the value 2, which is okay. And after that, something happens. I'm going to tell you very shortly. So that's why it means that W equal to 0 is a discrete point, but until I reach 1, the distribution function is going to retain the value 3 by 28 throughout. As soon as it reaches 1, that means I'm talking about this portion. As soon as it takes the value 1, that means W equal to 1, it takes the value 9 by 14. Okay, we calculated it. FW came out to be 9 by 14. So we substituted that, and it is going to remain as 9 by 14 until W reaches to 2. Okay, now observe what I have written in the last part. Last part, that means I'm interested in finding out the distribution function value when W equal to 2. But what happens, because we are actually considering the entire real space, real line, for which the probability function or the distribution function is defined. So the left hand side of 0, this portion, in this particular portion, the probability is 0. So nothing is there. On the right hand side of 2, that means this portion, the probability is going to retain the value 1. So the curve will be like this. So if this is the value, then next value is this one, then next value is this one, and then throughout the problem it is going to retain the same probability. So therefore, in this particular case, in this particular part, we have written small w greater than or equal to 2, because the distribution function is going to retain the value 1 throughout. So now let me show you the plot of the function that I have constructed. These are all rough works. So let me show you the actual figure. Just a minute. So here is your graph. So this is the graph. So this is the, and you see that this dotted line means a kind of discontinuity is breaking. Is a kind of discontinuity. It is a step function. Okay, ever increasing step function. So from 0 to 1, for this entire time, entire region, the probability FW distribution function is also a type of probability, but it is a cumulative probability. Now this may be asked in the examination to make you confused. They may ask you which of the following statement is true or false. So they may ask you in the option that distribution function is not a probability. It is wrong. Distribution function is also a kind of probability, but it is a cumulative probability. So probability has been the value 3 by 28 has been attained at the point 0, and the distribution function is going to retain this probability throughout until it reaches 1, and then it jumps to 0.9 by 14. It is going to retain 9 by 14 until it jumps at the point 2, and it is going to retain 1, and it remains throughout. So this is the thing. This is how a distribution function is calculated and it is plotted. Now in the examination, since we will be sitting for the online examination, in online examination, how the question can be posed, because the calculation is huge. So if there is an offline examination, what sort of question will come. If it is an online examination, then in that particular case, maybe this graph will be given to you, and from this graph you will be asked to identify the probability of the individual points. So this sort of questions can be asked in the examination. So you have to understand that what we have calculated. There is a difference between the probability function and the distribution function. If I want to plot the probabilities, for example, what sort of thing will get? If I want to plot the probability, we will get some this is your 0, this is your 1, this is your 2 point. Now at 0, the value is 3 by 28. So we will get a figure like this. You will get a line like this. At 1, some points, 9 by 14. That means which one is larger? So somewhere here point will come, and for 2, then the value was not 1, the value was how much? I forgot. What was the value? Let me scroll up. Oh, there were different values: 5 by 14, 15 by 28, and 3 by 28. Sorry, 5 by 14, 15 by 28, and 3 by 28. So just a minute. 5 by 14, 15 by 28, 3 by 28. So the values were 5 by 14, 15 by 28, and 3 by 28. Now, obviously, if I want to find out this 5 by 14 is equivalent to 10 by 28, and the value 3 by 28, I mean, if I consider this point, I'm roughly speaking. So this point is 10 by 28. No, this point, the figure I'm actually not drawing correctly. Just a minute. If I take, say, for example, this is your 0, this is your 1, and this is your 2, and this point is, say, 10 by 28. This point is, say, 15 by 28, and this point is, say, 3 by 28. Then for 0, 10 by 28, 15 by 28. So this point 5 by 14 was for the point W equal to 0. 15 by 28 was for the point W equal to 1, and 3 by 28 was for the point W equal to 2. So at W equal to 0, the value that we are going to get is this one. So a straight line will be drawn like this, 10 by 28. At W equal to 1, we are going to get a value which is 15 by 28. So we'll put a point over here, and a straight line will be dropped like this. And at point 2, we'll put a point at 3 by 28, and we'll drop a figure like this. So you see, we have got 3 vertical. These are vertical graphs. We have got vertical bar diagrams kind of thing. Line diagram. You can say this is a line diagram. So here we have got a kind of line diagram. If I compare these two figures together, you will see that there is a huge difference between these two. This figure and that figure they are not same. Probability function figure is a line diagram, but this is a step function kind of thing. This particular figure is coming from this line diagram, and this line diagram can also be generated from this particular figure by the definition of the distribution function. So the probability function and the distribution function, there is a kind of difference between these two. So this is the difference. Graphically, we can very easily we can understand what is the difference between the two functions, two types of functions coming from the same system. Now let's proceed. Okay. So another problem that I have actually given over here, this problem is something different. Here you see in this particular problem, the distribution function is given to you. This is the distribution function. Okay, so its diagram is a kind of step function. From this distribution function, we are actually supposed to find the probabilities. The probabilities are given as follows. First of all, they have asked us to calculate the probabilities, and then the probability distribution needs to be calculated. Now, the theorem that I wrote earlier, that theorem I have again written over here. So the theorem was this. So if you have a point, if you have a kind of range like this, that x1 is less than x2 less than x3 ... xn, then for this type of range, the first value of the probability's value at the first point will be same as the distribution function's value at that point. So if x1 is the first point, then f of x1 and capital F of x1, they will be same. Now, if we talk about the subsequent points, then at point 2, that I equal to 2, we'll write f of x2 is equal to distribution function's value at x equal to 2 minus the previous value, that is f of x1. So small of fx2 will be capital Fx2 minus capital Fx1, and so on. This is the formula by which from this particular distribution function, the probabilities will be calculated. So let's see how it comes out. So what I have done over here is that I have written all the points over here, because you see my points will start from 0 to 10. Why is it so? Just look at the distribution function. Just look at the distribution function. Distribution function, I have considered 0. You can consider 0 or you may not consider 0, doesn't matter. Actually, the lowest point is 1 and the highest point is 10. So I have calculated all the points over here. I mean 1, 2, 3, 4, 5, 6 up to 10. All the points I have written. Then the point px1, and obviously since at this no such point actually exists in the distribution function, obviously it is going to be 0, but we need to calculate it. Even if it starts from the point 1, we need to start from x equal to 0, the lowest limit. Now, if I consider x1 to be my first point, that is 0, then there is nothing wrong in it, because it is not contributing anything in the distribution function. So if px1 equal to 0, that means we are putting that value x1 equal to 0 over here, and p0 is the first value of the probability is same as the first value of the distribution function at that point. So f0 is definitely 0, because it is directly seen from the distribution function. So we have this. Now, if I need to calculate px2, then we will apply the formula. That's px2 means px1. I mean p of 1. P of 1 means the distribution function's value at x equal to 1 minus distribution function's value at the previous point, that is x equal to 0. And in this manner, we have calculated the probabilities. P of 1 means f of 1. F of 1 is 1/3. Just let us check. Let us check. You see, when x equal to 1, the point is 1/3. The f of 1 is 1/3. So from there, I'm picking the value and I'm putting it over here. So in this manner, we have calculated all the points, all the probabilities likewise. And ultimately, we have plotted all the probabilities over here. This is the probability at the individual points. So we have calculated all the probabilities and we have plotted these probabilities in the table. Now our job is to calculate and this is the probability function, this is the probability function because this is a discrete case, and probability functions you can if you the probabilities that has been asked is the probability actually in the problem you have been asked to find out the distribution, probability distribution. So this is the probability distribution, so points are there and the probabilities are there. Actually you can write here, although I have shown the probabilities only, so you can put one extra column. You can put one extra column and then you can write. You can just try. Let me try to do it. What I'm saying. Insert rows above. Okay, and there you can put a point 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So these are the values of x, and these are the you can write one thing more. Insert x. So these are the values of the probability x, the value of the random variable. These are the probabilities. These are the probabilities, and these are the values of the probabilities. So once you make this, once you write all these things, that means you have completed your distribution chart altogether, showing the values and the respective probabilities. Now it is just a matter of seconds for you to calculate the individual probabilities. So when it is probability, when we are talking about probability of x equal to 4, that means we are interested in P4, which is directly from the table, it is 1/6. And when we are talking about probability that x lies between 2 and 6, now you see x must be greater than 2, but it should be less than or equal to 6. So we have started counting from 3, because the discrete points lying between 2 and 6, including 6 and excluding 2, are 3, 4, 5, and 6. So we picked all the probabilities from the table and we have calculated the probability, which is equal to half. Now, once you calculate the probability, then what you can do, you can recalculate. Once you have got the values and the probabilities, you can calculate the expectation and variance, which I have left for you to calculate by yourself. I have also provided the formula for expectation and variance here and their properties also. Okay, so at this point, I'm going to stop today, and tomorrow we have a 2-period class. Then I'm going to discuss something.